Hello and welcome to Injection and Text Reloaded, tunneling malicious payloads through DNS. I'm Philipp Jeitner from the Technical University of Darmstadt and Fraunhofer SET, and this paper was written together with Haya Shulman, also from Fraunhofer SET. In this paper we show how to abuse the domain name system to tunnel malicious payloads into applications, and also to what type of vulnerabilities this can lead. So first, our motivation. General principle of the internet is to be strict when sending and tolerant when receiving. The DNS generally follows this internet principle, as resolvers should only basically interpret the data they need and pass any unknown data unchanged. However, this means that the validation must be handled by the endpoint, for example, the application which required the record. However, we know that applications are generally bad at handling unexpected inputs, especially if the developer doesn't actually know that an input can be present. So the question is, can we abuse the DNS transparency principle for attacks to tunnel malicious payloads into applications? First, we will look at a typical DNS resolution chain. First, there's an application which typically triggers a query which is forwarded to the name server. Then the name server provides a record in line format which can be any value, as we assume that the name server is controlled by the attacker. Then the resolver forwards the record to the subresolver and treats the data transparently as per the transparency principle. Finally, or not finally, there's a subresolver or a DNS library which translates the line format DNS data into textual form. Then finally, the application handles the data and processes whatever it needs. And now we will look at the three components, the resolver, the subresolver, and the application, what can go wrong there and what can make them potentially vulnerable to malicious injections. So first, we will look at the handling in DNS resolvers. We know that DNS resolvers should handle all the data transparently. So what is the problem? Essentially, there are two formats for domain names. There's the text format, which every one of you probably knows, where labels are separated with period signs. However, there's also the line format, where the labels are essentially represented as a list, and the length of each label is prepended to the label. So this means that actually labels can contain any value, which means that the label can contain period signs, which is kind of weird but valid, and they can also contain non-printable characters like 0 bytes, for example. And the point here is that the periods might be misinterpreted as a label separator, and the 0 byte, for example, might be misinterpreted as a string terminator. So the question is, basically, do resolvers handle the DNS data transparently, or might they stumble upon these special cases? To see this, we conducted an in-lab study first with 11 resolvers and found that all of them handle the data transparently. However, we then tested public resolvers and found that 1 out of 11 misinterprets the period in label for a label separator. Also, we tested open resolvers in the wild from a census dataset and found that 8% of them are vulnerable to a cache poisoning attack due to misinterpretation. So how does such an attack work? Here we have an example record set where we have a domain from the attacker, which is attacker.com, which cnames to victim.com, then a 0 byte .attacker.com. And essentially the point here is that if the 0 byte is misinterpreted for a string terminator, the vulnerable resolver might interpret it as victim.com has the address 6666, which is the address of the attacker, of course. And so now, if we do the injection, we ask the resolver for attacker.com, which makes it process the record and might cache it in the misinterpreted form. And then the validation, where the resolver is asked for victim.com, and if it is vulnerable, it will answer with victim.com has the IP address 6666 instead of 1111, which is the actual address of victim.com. So this was in resolvers. So what can happen in subresolvers? Essentially, subresolvers can have the same problems as resolvers, as they basically convert the line format data to the text format. However, there are other problems as well, because there's basically a difference between domain names and host names. As we know, domain names can contain any data, and the resolvers don't filter them. However, There's also something called a host name. The host name can actually only contain alphanumeric characters, dots, and hyphens. And the POSIX standard, which essentially standardizes subresolver functionality, says that libc resolvers at least operate on host names, not domain names. So we conclude that subresolvers should validate if the domain name is actually also a valid host name. So the question is if they do. To see this, we essentially tested 10 different implementations where 7 of them are libc resolvers and 3 of them are other DNS subresolvers. And they found that only 1 out of 10 validates and that 7 out of 10 misinterpret the 0 or period payload for a string terminator or label separator. Finally, we also tested handling in applications. We know that subresolvers don't validate if a domain name is a valid host name. So to prevent an attack, the application has to do it. However, for an application, it might seem that the DNS data is trusted because it comes from the operating system. Also, application developers aren't typically DNS developers, so they might not be aware of the specialities of the DNS standard, which values a DNS record might contain and which values it might not contain. So basically, we wanted to find out if applications validate DNS input, and if they not do, are they vulnerable to injection attacks? And to see this, we tested 16 different applications from different contexts and different DNS use cases. For example, address lookups, peer discovery lookups, burst lookups, and authentication lookups. And our findings were that actually none of the applications we tested validated the DNS data in some form that they basically handle them special. And also we found that 8 applications had vulnerabilities due to this. For example, cross-site scripting attacks, stack overflows, or buffer overflows. So what makes an application vulnerable? Essentially, for an application to be vulnerable, first the attacker must be able to trigger a DNS query. For example, if you send a mail to a mail server, the mail server needs to find out where the mail should go to, and therefore it asks the DNS. Also, the query result, which is received by the application, must be used in some context where an injection attack is possible. For example, it might be included in an HTML website. It might be saved into a cache where it can be basically misinterpreted, or it might be used in some inter-process communication. And so for some examples, we found 2 vulnerabilities. One was a cross-site scripting attack into OpenWrt, where you can basically do a cross-site scripting or inject the cross-site scripting payload via a reverse DNS record into a PTR record type, and it goes directly into the administrative interface of the OpenWrt router, which lets the attacker essentially gain control of the router because the browser in this case is logged into the router and therefore controls the router and can even flash the operating system. We also found some weaker attacks, for example, an ANSI escape code injection into the Windows ping utility, which might be able to lead the user to do some weird things because you can reformat the console output. And so finally, for our conclusions, we found that misinterpretations and wrong DNS processing all the way through the DNS resolver chain. We also found that the standardization for subresolvers is somewhat lacking, because the POSIX standard only defines that libc resolvers operate on host names, but it doesn't actually specify what a host name can be. To find out what a host name can be, you actually have to find the RFC, which is pretty old, and find that it is still valid for this definition. Also, we found that there's missing knowledge in application developers because many of them don't actually know the differences between the DNS line format, the text format, and the host name specification. And so they are not aware that these differences might be used to cause vulnerabilities. Also, we found that some developers aren't even aware that input from the DNS is untrusted and that they must check it. Finally, for mitigations, the vulnerabilities we found in applications are now fixed, and subresolver developers mostly agree to us that hostname checking is something they should do, so that the subresolver is essentially the component which should see if a domain name is a valid hostname. Finally, for the resolver attack, we developed a website where you can test your resolver if it is vulnerable to one of the cache poisoning attacks. Thanks for your attention and goodbye.